Thanks to join us today and to participate at this workshop. We will go through a little bit of part of history, but we'll make it. We will try to make it fancy. And thanks to Saumil and to Ring Zero to host us. Okay, let me put the presentation. Oh, small spoiler. Okay, sorry. And let's introduce us for a couple of minutes. So my name is Silvio. With Antonio, we work together in Leonardo. That is an Italian multinational company working on cybersecurity as well. And before Leonardo, I stayed in RSA and Symantec doing working as malware reverse engineering, and I participate on the design of VCAT as well. Previous to that, I started my career in cybersecurity doing a PhD at the University of Pisa in network security. Basically, the main topic was malware as well. So today now is more than 15 years that I am working. I started in 2006, looking malware and malicious code. So it is a while, but I'm still not boring at all on that. With Antonio, we create our own company as well. That the main focus is on doing red team tools, developing red team tools to make stronger the blue team as well. Please, Anto.
Yeah. Hi, everybody. My name is Antonio. I started as an academic career. So I got my PhD in system security, but then I moved to more practical things. And I worked for several years as a cyber threat analyst. So I had the chance to reverse engineering and analyze complex cyber threats, writing reports, writing decryption tools, stuff like that. Then I joined this in Leonardo company. Silvio said before, we met during this work experience, and then we found this new company, Retooling. It's called Retooling, and it's just a couple of months that we started this project, but officially, but we are working on it since more time. Yeah.
Yeah. So our training at Ring Zero, as Samuel said, is a larger. We'll cover more topics on malware. It is 4 days of training. It is really hands-on, so it is maybe more than 50% of labs. We designed it. We started with the idea of just focus on advanced techniques, looking and reversing malware. But while we was doing the exercise, planning the labs and whatever, it was not so a good approach doing that, because at the end of the day, the malware is packed, we cannot interact the data with the malware. So we start a new type of approach on that, changing the shape of the training. So basically, we started implementing piece of the malware to make a student practice directly with them. So it means that for each techniques that we will cover, we basically will have a source code that we is the base, and we will make these techniques stronger and stronger, putting at the to-day edge of real implementation. The training, we designed the training at the beginning just for reverse engineer, malware analyst, but at the end of the day, we discovered that this training is even good, and we had a lot, I think more than half part of our students that come from red team world. They are a guy that want to do to develop their tool and to do their job without using open source or commercial tools. So in these 4 days, we will cover basically everything, starting from the dynamic API resolution from the malware. We will cover the obfuscation. We will talk about basic obfuscation stuff. through the use of LLVM. We will talk as well about loaders, custom open source loaders used in malware, or alternative or custom implemented loaders. We will spend maybe more than half days talking about injection. We will see different injection technique, and we will talk more and re-implementing part of the reflective loader as today is used by crime and APT as well. And we will talk as well about anti-debug and the anti-VM, not all the common tricks, but the way that you can design anti-debug or anti-VM piece of code. So we will cover a little bit part of persistence and local privilege escalation as well. And for each of these topics, we will talk about the security mechanism that Microsoft or security vendor are trying to put in place to impairing the malware activity as well. We will talk as well for the use of different type of language to run malware chains. I mean, using C to run .NET, or using a PowerShell to run C, to run .NET, to run Go, or whatever you want. We will talk about ATW and all the bypass that is beyond that. And at the end, we will have 3 or 4 hours with the final lab where our student will design a custom module for implant that is doing a lot of stuff and putting all this part together. Just I want to remark that all the code that we will go through is code taken from real malware that we spend time reversing and implementing it until the code is really similar to the original binary. I mean, so we reverse, write the code, build, see that it's similar to the malware. It's not changing the source code again until we have something that is really, really similar, or at least identical, I won't say.
Silvio,
yeah?
Sorry to interrupt. There's a question on the chat. What would be an example of an alternative loader, something in Go?
Yeah, when we talk about loader, we are talking about just the Windows loader. I mean, in this particular case, we are re-implementing what the Windows loader is doing in C. There are different open source projects that attackers use during different campaigns, such memory module or dark loader or whatever, something like that. So it is more on re-implementing the original Windows loader and put it inside your re-implant to load at runtime custom mode. Otherwise, you can, we saw even some actors that changed the header of the PE just to make difficult the reverse engineer part. So this part of as well of the custom loader chapter. Ando, do you want to add something?
No, I think you went pretty good.
Thank you. So I hope I answered to the question, and so let's go ahead. So the workshop today, we will go through the. We'll start doing a little bit part of its history, talking, showing us some APTs. I don't want to talk about crimes because in this world of malicious code, the one that's doing research on making the malware better usually are the APTs because they invest time, invest money, and they basically shape the road that the other follow. So there we will get five examples of APTs just to show you the evolution that this the code has in the last 10 years. I don't I did not want to go so back in time because I can start this history around the 90s, but it is, I won't say prehistoric, malware prehistoric. So it is just already malware archaeology. For the prehistoric stuff, we can have a beer in the evening after the course if you want to talk about 90s malware. After that, we will show what make easy the analyst's life and what make the malware bad time. So we will talk about all the countermeasures that the operating system and the security product are put in place to make the malware life really bad. And after, Antonio will do a live session reversing a piece of Windows operating system, a really important piece. And at the end, we will show a small bypass that we did applying just the techniques that we explained in the first 2 days of our trainings. So let's start. Please feel free to ask any question on the chat or raise your hands and talk with us. So the first malware that I want, APT that I want talk about is APT1. So APT1 is this history. It was, the report was published by Mandiant in 2013. And in the report, you will find more than 1,000 hash of samples. So they collect more than 40 malware families. There was tons of IP or domains, certificate, and whatever. So the report is really long, and there was really a lot of IOC in the report itself. If we are just doing this exercise of archaeology, I went to VirusTotal, and from this 1,000 sample, I just was able to find 380 of them. Looking at this sample is really a huge group and of malware. Most of them has a size that is between 8 kilobytes and 100,000 kilobytes. There are as well open source tools such as Mimikatz or something similar to Mimikatz that was really common in this period. The campaign started in 2006, I think, the last sample. There was, at the time, there was basically no OPSEC. They did not use any kind of obfuscation. They use just, I won't say, simple tricks, such as putting the PDF icon inside the malware resource, just to show the icon to make the malware appear as a PDF. And the analyzing this sample is more, I won't say quite easy. It was self-explanatory. Just I can show you something if I find my virtual machine. Yeah. Okay. So, for example, this one is no, it's the wrong sample. Switch. Oh. Okay. Okay. So this one is APT1 sample. As you can see there, we have basically everything in clear. It's basically loading the library to connect with the internet. It has the user agent string put in clear, and it basically has a sort of decrypt code. This one is my comment that because I already decrypted the code. If we go there, what we can see is just that it is loading a string from the sample itself, and you can spot this one easily looking at the resource of the sample. If my machine gets okay, and this is the sample. So there we will see, if we give a look, we have the string table, and in the string table there is a resource that is this one, and this one basically it is the string that is going to decrypt. The algorithm that they are using is basically is based on a substitution. Substitution. If you go there, you will see the implementation of this substitution algorithm, and this is the string that they use as key. That is the quick brown fox blah blah that you can find in our old book of cryptography as example. So they get this code and put inside the malware itself. Going back, after the decryption, you have just a base64 decode, and this one will get out our string with the domain. If we go back to the main of the symbol itself, what we will see is that the symbol is just getting the system directory. And here we will have the command processing. So the malware will go to the connect to the C2, read the command, and process the command, decrypting the base64, and he is just comparing that with some strings that he has inside. And if we can make it more readable using our decompiler, bigger. Okay, with the compiler, the bigger it's not working, but so there you have all the string that is just saying active, wait, that is the session that the malware is established with the C2. And we have as well error message such as create process fail. You have basic the processing with the C2. So when he has active, is just able, the symbol is just able to execute a command using the CMD, and he's just getting the create two threads, one to communicate back to the C2 the results. So there is any kind of real obfuscation or encryption, or even the other symbol that they created that is always from the same family. Should be this one. Okay. Here you have directly the IP that is going to use as C2 with the port, and at the end directly you have the sleep, the infinite loop with the sleep, and the thread that is this one is the one that is doing the main job with the interacting with the C2. In this case, they are not using the HTTP function, but they are using the low-level function. So I mean, connect, the send, and the receive itself, and the receive API. So here as well, you have the interaction, and the interaction is you can spot what this symbol is doing, just decrypting some strings that he has inside, that correspond to the command that is just trying to see if a string compare. So what I mean is let me go back. Okay. So what I mean is just the command that is able to execute is CMD, that the original string is just base64 with unsupported sleep and quit. So just anything that was, this is just small piece of code that has a specific job to the made to make a specific job, and they basically does not care to use any really OPSEC at the time of this symbol writing. So let's go ahead to the next family. Okay. So the next sample that we want to talk about is Strider, that was published from Symantec in 2016. It is that is another kind of malware. It is an APT as well, and it is a framework for long espionage. So what this framework does is extremely modularity. It has a rootkit component that was loaded through a vulnerable driver that supports even 32 and 64 bits architecture. All the module and all the network protocol was encrypting using different algorithms. So it means that all the traffic that is passing is not just base64, but there is an encryption with a key, a session key, and even the symbol itself has a different layer of encryption. So it is not so easy to reverse, or it is not so straight that you can spot what the symbol is doing. Another stuff that it was interesting for this kind of sample is the use of Lua. So they basically re-implemented the part of the Lua engine to create plugins, easy plugin to develop in a fast way plugins that they as a specific do specific action in the machine. So they develop more than 50 plugins. The idea, they want to control an entire network, so there is just not a directly machine, but they infected the domain controller, and from the domain controller, they can jump in any machine of the network that the attacker wants to have visibility. Even when they jump, they use a really small piece of samples that is more than 5 kilobytes that was used to download the main part. They use as well a small tiny module that is used to exfiltrate file from air-gapped network. So there are a couple of reports on the internet, one from Symantec, another one from Kaspersky, that did a really good job describing this threat actor and all the architecture they used. So it was interesting the persistence that the sample used, because they registered a module on the Windows Local System Authority, so the LSA basically, as password filter. When normally these modules are written from sysadmin to define the policy of password for a network user. So basically doing that, you can say, I want a password that is longer than 16 character with all question mark, caps and no caps, and so on. What the attacker did is just to create malicious module that is loaded inside this Windows component on the domain controller. So every time a user log in, it will execute back the malware on the machine, on the domain controller, because it is LSA that is just infected as well. So this is a really unique feature, and they just show what is the main aim of the attacker. They also implemented a virtual file system to store the plugins, to all the data, and all the utils that they use. Another really good OPSEC feature is the vector that was passive. So it means that the vector will not be beaconing outside, except the attacker will not activate the vector itself. And there, another stuff that make this malware really important on the history is that each node is able to be proxy for other nodes. So it is creating, the malware is able to create a peer-to-peer network of implants, and making the implants that are not directly exposed to internet reachable from outside. So that was really a really good feature. So if we give a look to the sample, virtual machine, please help me. I can show you something that. Okay, this one was one of the Sauron sample. As you can see, we have here a really small number of functions and a huge amount of encrypted data. So if we jump in, we will see there that it's just binary data that has no meaning. And this symbol is a part of the Lua engine. And what it does basically is exposing three exports just to mimic something related to the password. And if we go to the password change notification, it's the bad routine that I did not click. And this one is the real routine that it is used. If we go back there, it's just doing basic stuff of memory. And here we will have the decryption part. So it's parsing the PA just to jump at the end of the PA to find the bin section. And in the bin section, it has a function that is it is a small function, really small function, that is this one, that is used to decrypt the symbol itself. So this one is a DLL, but I modified it, did a little bit of tweak on it to make it look like an executable and run using IDA directly without taking care about the service and all the checks that I should do normally to execute it. What you see there is just that if I jump in at this initial function, move the extraction pointer, I can directly go to the decryption function where I put my breakpoint. And here you will see that it's jumping on the bin part where we have the decryption function that I show you at the beginning, that is this one. Let's make it calling. And there, let me try, yeah, I cannot make it bigger, but I can try to do something like that. Yeah. There, this one is a sort of position independent code. So you will have the call $+5, that means plus the pop, that is just a way to get back the extraction pointer that is commonly used on shellcode. And this one will go directly to our decryption routine. Okay, yeah, I know that I hit my breakpoint. And go ahead. And if I go ahead, there is just calculating the point where it starts to need to decrypt. So I mean the binary. I already executed the decryption function, and now it's just jumping on the code that it decrypted. So either it's showing us as bad code, and yeah. So now it's making the code clear, and this stuff will be, is not just the final stuff, but it will go through different layers of decryption. So if you want to see the final payload, this payload is packed. You need to pass through different layers. They use different algorithms between RC4, RC5, or SALSA are the most two that is used to encrypt the first two layers in most of this symbol campaign. This technique is used in other different symbols of Sauron or Strider, depending on how you want to call him. And in other symbol, you will see this kind of behavior. So you have a really small amount of data with, this one is another symbol of Sauron, a small amount of function with the same stuff. So you have the function that is used to decrypt, that is called at the end, and you have the small tiny shellcode that is doing the job I show you. So this one has another philosophy. They make it really modular. There is pieces that communicate talk together to make the entire malware working. And they also reduced the detection surface, creating this plugin using Lua. So if you just get a piece of this malware, you did not burn the entire operation, or you need maybe an infected machine, or better, an infected network to try to understand the entire behavior of the attacker itself. So it is another design with another concept beyond it. And this make another shape, another evolution in our story. So let's go to another family that is called the Connie, and it was published in 2017 from Talos, from a friend of us, Paul Rascagni, and this actor was active since 2014. They use another approach different to the previous one. They have a piece of code that do some basic functionality that is used just to steal information from an infected target. I mean, keylogger, clipboard, and exfiltration of browser data. So probably password or visited website, or all the cookies with the session key tokens, whatever. This malware write a lot of file in temporary file on the disk, even the keylogger file as well. And they do not use really strong encryption, but there is an evolution. So if we give a look to these two samples, one from 2014 with the one 2017, they changed a little bit, making the implant better, changing the network communication API that they use, and they introduced other functionality that make the RAT complete. So I mean, such as download, upload, and execution of arbitrary commands. So the sample is just really easy to analyze. Just it was just remember bad. Yep. This one is 2014. It's similar with the APT1, so it is loading a string from the resource, get the system directory, because the old version use the system directory as home. It generates a malware ID using the install data. They get the installed data looking at a key, registration key that they write during when the malware is dropped on the disk. So, and it is used as a basic to generate the sample ID that it is used to register with the C2. For exfiltrate all the browser data, looking at all the registry that the machine has inside its folder, and pack it back and write on one of the temporary file that it opened on the disk. So as you can see here, you have a lot of strings, a lot of API, any really obfuscation or encryption that make the analysis more complicated. So this one is opening the file that is using as keylogger, and the sample basically that's it. There's anything more. So you have a lot of library function that they imported and it's implemented statically inside the sample, and that's it. You have just everything is here. Where if we want to see the communication part, we can just search for see if I remember act. we can go look the connect. And if we do xref with the connect, we can see the connection function that is the one that responsible for talking with C2. This one is referenced by, it is on C2 init function you have here, and you have the domain that you use to the C2 domains that for each symbol, the old one has 2 C2 domain, and the last one you have just 1 C2 domain, and this function is called directly from the main. From the main, there is a infinite loop that make it call with a sleep beyond the beacon time that is fixed, and this one is called directly from the main. Come on, go back to the main. Yeah, this is the screenshot that I said. This is it is connected with called using set Windows hook API, and this one jump back to the main. Yeah, exactly. That is here. So the 2007 version is identical. Is exactly the same, except that they changed the function used to connect using Internet Open instead of the USA basic function. Here we have just 1 C2 instead of 2, and at the end of that there is this function is used to interact with the C2, and there is a processing command function that we can spot easily. Yeah. So okay. So here we see the init of all the temporary file that this symbol wrote right on the disk, and they try to open the directory, and there is the thread that is just interacting with the C2. This one is the one used for the keylogger, if I don't remember bad. Yes. And with the C2, yeah, the command processing is this. Yeah. And here, here you have the switch with all the 7 commands that this symbol is able to execute. So get fingerprint machine, do a screenshot using the GDI API, and upload the file using a relative path, upload the file using a full path, and remove file from the disk, and just sleep and wait for next beacon time. So this one is just another example of, it's not a regression, but it's an evolution from another threat actor, and this symbol has a different aims between, that is quite different from the Strider symbol. Go to something more fresh. We can talk about the Ghost Emperor that was published during the SAS, the Security Analyst Summit in 2021. It is a multi-component toolkit with a long infection chain, with a rootkit, really interesting rootkit, and it use different language to develop their tool. So you have C, C++, .NET, and PowerShell. They started to use obfuscation using LLVM, and they have a SDK to that change some code during the when they built to make some kind of obfuscation inside the sample. They use execution guardrails to avoid that the sample will be run outside the infected machine, and they create a sort of spiring the Cobalt Strike malleable SHA-2 profile. They just implemented something like that to reshape the traffic that the symbol is able to generate. Depending on the impact of the machine, they try to make the traffic similar to one of the legitimate application that is running on the machine. When they send outside the exfiltrate data, they use to create a sort of the header of image files such as PNG or JPEG, and put an encrypted blob inside the image. So if you look at the image seems very valid, but the image itself is just there is any representation or any good image, you will see just a random pixel inside the image. But for just to evade perimeteral firewall or traffic analysis system, that was just enough. It is able to load in memory arbitrary .NET assembly and execute the PowerShell command. They also implemented the remote desktop protocol without using the remote desktop application or protocol, the real protocol. That make it having the RDP without using the RDP. That is really a good feature. For talking a little bit about the driver, considering that it works until Windows 10, I think, and with Windows 10, Microsoft introduced in the last previous version, I mean from Windows 8.1, Microsoft introduced PatchGuard and driver signature enforcement. So you cannot load unsigned driver, and you cannot touch anymore the internal kernel structure. Otherwise, PatchGuard will make the machine blue screen. So they use a cheat engine signed driver, and they misuse the cheat engine signed driver. And what they using this driver, they are able to allocate a buffer in kernel space. And with this buffer allocate, they copy the rootkit inside this buffer, and they patch the dispatcher of the cheat engine driver, making it pointing to the rootkit IOCTL. So the rootkit IOCTL function is a position independent code that make them independent where this buffer is allocated in kernel space. So in this way, they basically rehooked the driver that they used to load the rootkit itself. So there is any spare memory that can be, there is any driver more than the cheat engine driver loaded in the machine. The rootkit was able to hide the file of the user space, registry key, network traffic, and place a callback inside the PCI.sys legitimate driver that will do some part of this job. So there are the symbol are obfuscated. There are a lot of anti-analysis tricks implemented, and even the drop and the loading procedure is a long chain that make different steps to have it works. So just to show you something, example from this campaign. Okay, it's 64. Okay, this one is the main of one of the service that is used to load the driver, that they obfuscated using LLVM. If you see the call graph here is really big, huge, and either if I try to decompile it, will generate, will take it some time to decompile, and at the end you will see while one, nested one, one inside the other. So my machine is asking me mercy. Okay. Yeah. So this code is not human generated code, but is code generated by LLVM. During our class, we will spend a lot of time talking about LLVM and doing exercise of obfuscation, generating obfuscation about in our symbol using these features. So the obfuscation that they did is not perfect because they left, as you can see here, different strings and different APIs around the code that at the end of the day, if you start to look at this symbol, make your life a little bit easier analyzing it. You will miss some part that is between the call. Maybe you miss the parameters, but what the code is doing is not so obscure. The symbol itself is not so big. Another technique that they used,
Silvio,
yeah?
Let me add something just about the LLVM obfuscation part. Something that we do actually is taking the original code, let's say any code. We provide our own toy implant provided during the training, and what we do is actually taking the code, taking the original code, and without touching it, where we generate this kind of obfuscation at intermediate representation through LLVM in order to get something which is similar to the one that you see inside IDA, which correspond to a real implementation used by a real detector on real attacks. But what we try to do is actually to avoid this kind of OPSEC mistakes or obfuscation mistakes in this case, and try to avoid, placing clear text strings inside the most critical part of your code, and just leaving their readable string that are not telling too much about what your implant is actually doing. And I think the same happen also for other techniques that are implemented also by Ghost Emperor, such as the multi-lang part. Also, that one is covered by our training. We covered that part. We have these features, and we keep adding features each day of the training, just to make things starting from something simple and make it harder and harder to analyze, to reverse, and to detect as well. Just wanted to add that, please.
Yeah, exactly. We will start from something that is similar to the APT1 sample, and we will end up with something that is more similar to Ghost Emperor or the last one that I will show you sample. This is another sample of Ghost Emperor that is using other LLVM tricks to do obfuscation on the code. That is, they try to make a little bit messy doing with the API that they are trying to resolve at runtime. If I try to decompile it, this one will be decompiled. No, failure because the function is too big. So even IDA said, no, I cannot do that. But you can use a solver to try to make the code back to the original one if they use the not so hard to reverse obfuscation LLVM techniques. So let me go to the last sample that I want to talk, and I will complete the history, malware history. So this is a really recent report that came out on June of this year of APT that is active since 2020. It is a multi-stage loading process through different language. Basically, they have 2 or 3 loaders depending the version that are C++ implant. That is, they are used to load a .NET. And the final backdoor, they use 2 different backdoors that are .NET backdoors. Even when they load the common language runtime, they use a teeny .NET loader that will load the original backdoor. They use API call obfuscation, the C part, and the traffic is blended with the not malicious traffic of the server. Typically, this implant is used in the victim or a web server or something that is exposed some service, and they use the .NET HTTP listener class that is belong to http.sys to allow 2 different processes to share the same port. So they did not open another port. You have always the original port open, and the traffic when is passed to both the application, and they search for a signature, specific signature on the traffic to get the packet for the implant instead of passing to the legitimate application. So the C2 use multi-protocol with traffic shaping similar to the previous one, such as ICMP, DNS, or HTTP. Another nice feature, let me pass the term nice feature, is the working hour. So the attacker can say the implant to communicate to specific time range of the day, saying maybe stay active between the 8 and 5, so that is office working time, and where there is more traffic and there is less probability to be discovered. They implemented as well a proxy mechanism, so an implant that can be a proxy from another implant, and they have different process injection techniques. So they can inject code in other process, or the implant itself to the other process. All the implant itself is divided in different pieces, and each pieces depend on the previous one. So the installer, it's really tiny. It is 90 kilobytes, but there is not the payload inside it. It needs another file that is XML or PNG or TXT file. That is a binary file with and encrypted the real payload. The installer create a couple of registry key, and this registry key will be and DLL, and the DLL basically is the first one that is executed by the installer that will read back the registry key and will decrypt in memory the second part of the loader, and that will go ahead until the last part, that is the one that is instantiated the .NET framework to run directly the assembler with the final backdoor that is named Samurai or Ninja, depending on the version you are looking on. Let me show you a little bit an example of this sample. What was the little bit? There. No, 64. Yeah, this one. So here we have a piece of code that is doing it is reading the file. It is reading the file, and get the sites, check for a specific signature, or if the file, this is the magic that the file should have, and it is used to load and decrypt the file itself. So at runtime, we do pad walk. It is technique that we as well will cover during the course, and they will load the library at the end of this function. The same will be done for get proc address, and with these two API, they can do the other part can execute the other part of the job. What you see there is that they use import by hash, that they have these constant that are around the code that will be used to decrypt the function. So, okay, yeah, this constant corresponds to a crypt acquire context function, and the code here, that is this one that I call the get by hash, is responsible for load the library, get a pointer to the library, and search, go through all exports, and reapply the hash function, comparing that it is the same with the one that is looking for, and it will be imported by the using the get proc address pointers, and making back and populating the global variable that contains this pointer. So this technique is quite common. They use does not use any common hash algorithm, but they use a XOR based hash algorithm. So if I don't remember bad. So this code at the end is used to decrypt the registry content and to run the next loader. The next loader is this one. That is the one that is registered as a service, and it is responsible for loading the common language runtime for the next stage. So the function that will load the runtime is this one. Yeah, and they try to see if there is installed the version 2 or version 4 of the runtime, and they start to make it sync with. And they will use core bin to load the runtime version 2, or if they go to the version 4, they will create a safe array and use the core initialize API function revector on get string, and where is yeah. Maybe it's one inside one of this function. Okay, that is the core bin. Let me find it in easy way. No. Okay, it's like, yeah, CLR create distance. Okay, I miss it. Yeah, it was at the beginning of the function. I am going crazy with the Zoom and the Zoom mobile. So here we have the co-initialize CLR create that is used to basically to load the version 4 of the runtime. So even this part we will cover doing exercise on this kind of implementation. We have something similar, really similar code, because it is a standard used by different threat actors or in different red team toolkit that is used to have a .NET runtime itself. So go back. That will complete our malware history. And what we discovered during our history passion is that our history walkthrough is that there are something that make really easy the analysis, such as the compile timestamp, the entropy, the section, the quantity, the amount of code, the amount of data. I used different times the import address table to find function or piece of code with command processing, or the part where to connect with the C2. So even the API talk a lot, or we're using the cross-reference from IDA. The human readable artifact tell us more again. For example, they give us the API that can be loaded at runtime, or the C2 address, or if they use the debug message, we saw the debug message saying that the command is unsupported, or the keylogger string that they put inside the text files. So all this human readable artifact is really easy to use and make detection rate on Yara. The pure binary symbol are really more difficult to reverse it, to analyze. As well, the export table tell us a lot, depending on the malware it is trying to mimic a good library. In the case of, for example, of Sauron example, and depending even for encrypted or packed malware, depending even the disassembly that we are using that make our life easier or more complicated. There we have a couple of information of the type of binary disassembly that tools implements. Even the control flow graph tell us a lot of information, saying a lot of information to skilled analysts. So this is a typical CFG if statement. You have the for statement that is released to spot, as well as the while, and the switch statement, the switch statement. For huge implants with a lot of commands, you have this command processing that is really big. But from that, depending, if you go to the last part here, you will have the functionality that are typically implemented is in this part of the call graph. We see different kind of encryption that are XOR based, that typically are just tricks to remove encoded strings from the implant itself. So we did during our journey, we talked about packed and obfuscated. So the packed symbol are the ones that are encrypted with a big data section, and the obfuscated instead is a poor code, but the code is really hard to analyze directly, or you need to lift the code a little bit to understand what's going on. So why people, APTs, crime spend time to implement tool or to make the tool stealthier, better, or whatever? So basically, the malware code go at the same step by step with the defender. So more the defense is doing, more the malware code the malware code needs to be more complex to evade detection to remain undetected. So during 2017, with the file creator updates, Microsoft introduced the Windows Defender Exploit Guard. That is a complete suite to raise the protection of Windows systems. It is divided in 3 big pieces. The one that we need to look more is the exploit prevention, because doing the apply techniques such process injection and ROP or something similar to like that fall inside the. It's more likely you will hit the exploit prevention security mechanism. So in Windows, the exploit prevention, there is DEP, ASR, control flow guard that avoid the code to jump around a piece that is not thinked to be jumped. We have the code identity guard that restrict the loading of images signed by Microsoft or higher. We have the export address filter, import address filter, that is a way to avoid that application be victim of hooking, external hooking. There is anti-ROP mechanism, and all that is implemented inside the APT console. Let me, I am going a little bit longer, so just saying 2 words that Antonio will use in the second part of the workshop about control flow guard. Control flow guard is implemented in 2 sides. It is implemented at compile time, at runtime. At compile time, you need to specify a compile directive to have your sample protected by control flow guard. And at runtime, the kernel will double check that everything is going as designed. So what happens is that at the compile time, it calculates a bitmap with all the possible jump that can be done inside your application. And when there is a call or a jump at runtime, the kernel say, we'll double check with this bitmap and see if the jump is allowed or it is forbidden. So when it is forbidden, when someone do mess with your application, and typically you just inject the code inside or overwrite piece of code, and so the jump are not be compliant with the BMP. What you will see in IDA there is you will see the guard dispatch I call that will be resolved at runtime by the loader, and the loader will resolve through LDR query process module info. That is the one that implement the double check with the bitmap. In this function are exported by NTDLL, so CFG is inside the NTDLL itself. So there are a lot of security mechanisms that this operating system introduced during the time. Just to name some you have the USC, so the user account control that everybody I hope knows. You have the access token, security identifier, this ACL, DACL, ACE, and at the end of the day, they also introduced the integrity level, ELAM, and the PPL. So I will shut down for now and pass the floor to Antonio that will introduce more to ELAM and PPL stuff. So prepare your virtual machine and your WinDBG and enjoy the live session.
So can you see the slide? I guess everything is working correctly. Okay. So in this part, Silvio mentioned PPL and ELAM driver. So in this part of the talk, we will try to do a deep dive on this technique, but we will try to do this with a real example. So we found there's this tool, this called PPL dump, which is used to exploit actually a design flow to dump the memory of a protected process. We will see what a protected process is in a couple of minutes. But is something that you should not be allowed to do, at least with just administrator rights. So it's a security boundary between administrator rights and some specific protected process. The problem is that this PPL dump is a well-known tool, actually. So it got detected by Windows Defender if you try to run it. You're not even able to run because there is also static detection that prevent you from running this tool if you try to build it from sources. This is a public tool available on GitHub. So we will try to evade Defender signature in order to be able to run PPL dump, but we will try to do this automating, messing the code, but with some techniques that can be actually generalized. So we will start with a little bit of background knowledge about ELAM. ELAM is a security mechanism which is related to PPL. And this essentially allows third-party security vendors, such as AB vendors, to register a kernel driver that is executed at the early stages of the boot process. And one important feature is that it is executed before any other third party. And this allows this driver to have like a privileged position to measure all the driver while they are actually being loaded. And what an ELAM driver does is actually providing a classification and just tell to the Windows kernel, okay, I've checked this driver, this is bad, or I checked this driver, this is good. Please continue the loading process. But this is not much, exciting just to see this in a slide. It's better to just, open WinDebug as this process actually in action. So if you got the mail from the organization, you should be ready with the configuration in order to have your kernel debugger attached to the machine. So the first thing that I usually do is just to set my symbols directory like this. My symbols. And then usually I do a reload just to make sure that everything is synchronized. And that's it. So I just boot up the machine. I can show you where we are. We are here. It's just freezed here. So we are in the early stages of the boot process. And we can also verify this by looking at the call stack. And we can see that we are being called by the key system startup routine, which is one of the first routine which are executed after the system is booted. So after the bootloader. Okay, we are here and we want to find our entry point, the entry point of the ELAM driver, and in particular in this part we are interested on an ELAM driver that is installed on every Windows machine, which is actually the WD boot driver, which is the ELAM driver related to the Windows Defender product. So we are here, we are in the early stages of the boot, the driver hasn't been loaded, we want to find a way to actually get the moment when the driver is loaded in order to understand what actually does inside from a debugger, not just from IDA. How can we do that? So one way to do that is just target a routine which is called while any driver is loaded. And in this case, we can place simple breakpoint on this function, which is initialize built-in driver function. But this is a generic function, and we just want to be aware of the fact that exactly the WD boot driver is being loaded and not another driver. So how do we do that? So if we use the disassembly function like this, and with /c, we just get, in the code sites, we get all the call sites that start from this routine. So here there should be a moment where this function actually called the driver entry point, and it will be also the entry point of the WD boot driver. So this is the something that Silvio discussed about, which is about CFG guard. I can tell you that here is the right place to place your breakpoint to understand what is being loaded by this function, which driver. Okay, so if we place a breakpoint here and we just let it go, what we can see, we short it. Okay, this is not our breakpoint. It is a different thing. Okay, we got our breakpoint here. So how do we check if what is being loaded? We can use dx and just check if there is a driver object around, and we can do it like this. .rcx. Okay, we now know that there is this driver which is being loaded here because its driver name is WDF01000000. So we find a good place to actually see what driver is being loaded before it's actually being loaded. If we keep going, so after this point, the driver has been initialized. I mean, this driver here, the WDF driver. Of course, we are looking to the WD boot driver, right? Which the ELAM driver we are interested on. So these are all drivers that are actually being loaded before the ELAM driver, but these are all essentially Microsoft driver. So it's not really something an ELAM driver can care about. So we keep going. Now we got the CNG driver, this exposed cryptographic function. As you can imagine, these are important functions even for ELAM driver that has to check the other drivers before they are loaded. And in order to check that driver, for instance, it must compute some hashes or do some cryptography on the input. So this could be very important for an ELAM driver to use. So if we keep going, MSEC, another driver, SGRM agent, LXSS. Here we go. So the system is now ready to boot the WD boot driver. So this is the moment that we want to follow. Actually here we are not yet inside the entry point of the driver. We are not in the driver entry, but in order to reach the driver entry, we can do like this. So it's loading the symbols. We're actually now in the entry point of the driver. So one important thing to note, actually, is that this ELAM driver have actually reserved the registry key, which is this one. So it's /registry /machine /ELAM / in this case will be Windows. Okay, we queried this registry key, and we were able to do that because we are in the early stages of the boot. This registry key will not be accessible once the system is actually completed the boot. So this is the only point that we can actually use to understand what's inside this registry key. And this registry key contains this value name measure. And if you open the WD boot driver on EDA, you can see that it's actually accessing this registry key. And the reason why it's doing that is clear if you try to dump essentially the content of the address where the measured registry value is actually loaded. 1,000, I think it would be enough, 1,000 bytes. So you see all this blob here, but in order to understand, just have an idea, we don't have, don't time to understand the exact format of this, but you can see that here we can find something which is recognizable because it's a typical way of represent signature names inside the IV industry in general. So what is actually doing here, the ELAM driver is loading a base signature set to be checked, to be used to check the next driver that are being loaded. Then we talk about callback. So we say that ELAM driver has to register callback, but we didn't talk about how these callbacks are actually registered. So here we should mention one function, which is the IOP register boot driver callback. And the register group driver. Okay. Let me type. There wasn't the P, and the reason why there wasn't the P is actually that this function is it's not private. The P stands for private. And you can even have a look to it inside MSDN. You can see that it takes two parameters in input. One is the actual callback function, and the other one is the callback context. I can tell you that this one will be null in the case of Windows Defender. But this is the one that we are interested on because we will try to place a breakpoint here to see when actually the callback function is called while the driver are being loaded. And we can even have more information about also the prototype of the function directly from MSDN, because we can see that the first parameter is the callback context, that in our case will be probably null for all drivers. But then we have this classification data structure. Yes, the data structure is the callback type. And then we have the PBDCB image information, which is something which is very interesting because you have the definition here, and here you have the classification, which is actually the field that will be used by the ELAM driver to communicate to the Windows kernel if the driver has passed the check or not. So we place a breakpoint here to the function which is used to register the callback, and we can just let it go. Yes, it should stop soon. Okay, here we go. We say that the first parameter is actually the callback that is being registered. So we try to unassemble RCX, which is where the first parameter is placed. We can see that this is actually real code, good code. So we can be confident that this will be the callback function. So we can place a breakpoint here, maybe on RCX. Okay, there we go. Here is our breakpoints. And then we just let the driver run. All the boot process continue. Okay, we just got hit by the breakpoint. So here we can see that there should be a image information inside R8. Also. Okay, what's this? Okay. I had to reload the symbol. Probably I was missing something. Okay, that was the mistake I was trying. This is not an anti-host kernel symbol, but it's a symbol from WDF. In this case, okay, that's fine. we find that this is the type that we're interested on. The first is not a good one, but we can just go to the next one and disassemble it. Okay, there we go. So what we know here is that the WD boot is actually checking this driver. So the callback is being called before is Intel pep.sys is being actually loaded, before the driver entry point is being called of this driver. So here we can see the current classification. We can see also that we have information about the signer of the this particular .sys file and several other information about the certificate issuer. So here we are in the beginning of the callback. So there is still there is no good classification yet. But if we go to the end of the function like this, and we know that the result will be placed inside the F15, and we try to dump it like this. Okay, we can see that this driver here has been classified as a non-good image, so something which the NTOS kernel should like. Okay, but we can keep going and see that this will be called like for, this is not our breakpoint, this is breakpoint 0. We are interested in breakpoint 2, but should be the next one. Okay. And here we see that there is another driver which is going to be checked by the callback inside the Elam drive. And we can keep going like this. So as you can see, the first breakpoint that we placed is actually breakpoint 0, which is the IOP initialized built-in driver, which is the function that actually calls the driver entry. And we are being called with our callback before the driver entry of the driver has been called. Okay, that's the reason why we see that a breakpoint 0 hit just before the breakpoint 2 hit. Okay. So we can disable and let the boot process continue. So we should have now a general idea, a more precise idea of how Elam driver works, at least in the early stages of the boot. But this is something that is not just to check the early phases of the boot. Elam driver has also related to EPL, as we will see in a moment. This is just a reference of the classification stuff that we were just saying inside WinDebug. But I mean, we already talked about this. So another important thing about Elam is that there is inside the Elam driver, there is an Elam certificate. There's a specific resource which is embedded inside it. And this resource contains this structure that you can see on the left. This Microsoft Linux Certificate Info MS Elam Cert ID, Cert Info ID, which is like this. The one that you see in the bottom part of the slide, in the background, is from a security vendor. So you can see that the first byte is 3, which means that there will be 3 entries inside it, and you can see that you can recognize that there are actually 3 entries. I'll try to do this sign with my mouse. I don't promise that it will be very good. Okay, here you can see that all these hashes are actually separated by constant bytes, and then there is another string. That constant bytes are actually the certification hash algorithm, and the hash that you can see is actually correspond to the to-be signed hash, so a specific part of a certificate that must be used to sign the service that must be blessed by the ELAM certificate in order to run as a PPL, so as a protected process. So if you want to get this additional protection offered by the operating system, you need to have this ELAM driver, because if you're not Microsoft, then this will be the way. And one way to check, should have it one inside here. Oh, maybe I remove it. Just give me 1 second. I will go inside. It's not here. No, it's not here. So this is the certificate that we saw before. And these are the hashes that you found in the slide. And if we take the corresponding blessed, let's say, services, put it here. So this is a short command that has been developed by McGregor. Oh, sure. Forgot to disable the execution policy. Okay. Okay, and now I can just type this command here in order to have this information about the to-be signed hash. There should be a correspondence between this hash and the one which is stored inside the ELAM driver. So if I do this, yes, and then I try to get the authenticate signature. Yes, and I get the signer certificate property. And then I pass this to the hash. Okay. It's not part of the story here. Select the menu. Oh, it's not exclude product. It's expand product. I was excluding exactly what I was always that it was always intended to dump signer certificate. Okay, here we go. This is the certificate information, the to-be signed certificate information, which is related to the services, which is blessed by this ELAM driver. You can see here that there is this correspondence. So the first one, so here we run this command on this file here, which is the correspond to services, which the vendor, the security vendor, want to be run as a PPL. Whereas this here is the resource which is embedded inside the ELAM drive. So there must be this connection. Otherwise, the service won't start. Okay. So ELAMA is something which is related to PPL, and PPL is a security technology that has been introduced by Microsoft since at least PPL, Protected Process Lite in Windows 8.1, and this was based on a previous security measure that is called Protected Process, which is introduced in Vista, so before that one, and was originally developed to protect DRM content. So the idea is that you want to prevent reading the memory or code injection attack or whatever by non-protected process, even if they are running as with administrator privileges. And this security measure is enforced by the kernel. There are some bits inside the process that are actually dedicated to this, and you can again check this from in debug. So we can break here the execution, and we can just attach to the. I mean, you can check also this using Process Sucker, Process Explorer, or whatever. But here you can see actually where the information is stored. So I think it's more precise to some extent. So we can do like this, processes, and we can filter using the queue where P. There's some mess with my keyboard. Change keyboard layout. Okay. P dot kernel object dot. It's greater than 0. I think I placed some strange character inside KD. Is complaining. Oh, no. Okay. So essentially, we are asking, we are looking for processes where inside the process data structure, we have the protection level greater than 0. And we can see that there are all these processes here that are actually protected processes. We don't know which is protected process light or protected process, but we can see that just by looking at this information. If you want to see if one is a protected process or a PPL, we can try to look at, we can look at the type information, which is something which is stored here. So this field here will be equal to 2. Only for protected process and not for protected process light. So you can see that system process, registries process, MM compression process, and SGRM broker process are the only process that are PP protected process. The other ones are all PPL. We can find also LSAS here because while I was preparing the VM, I also added LSAS security protection mechanism, which allows you to run this as a PPL. But it is not the default. This is not the default configuration. These are mostly kernel-related process, and this is something to implement security features. In particular, use it to implement system guard when virtualization-based security is enabled. Yeah, let's go back one more to the slide. Here. So if that bit inside the process are set, actually, there are some limitation of what a non-protected process can do on a protected process, or a protected process, a non-protected process like can do, or a generic process can do on a PPL. So usually, you can do only, even with admin privileges, you can do only very limited tasks. I mean, you can overprocess with process query, limited information, or set limited information of process suspend resume. And not for all of them, you can even call process terminate. For some PPL, it won't be allowed to terminate the process from the with administrator privileges. And also, we said before that this process is also protected from the loading of non-signed DLL. So there is also a mechanism related to this, which is related to the code signing checks inside the of the DLL that must be loaded inside the process image in order to be able to run. And we will see that in a moment. Okay, so there is not just one PP, it's not 1-0. There are the so-called protection level. The strongest one is the one in the top of the table. So it's the PS protected system level, which is a protected process. So the first 4 entries are all protected process. The last ones are all PPL process. But for both of them, you can find different signer level and different access privileges, I would say. So there is an additional e-process field that I was mentioning before, which is the section signature level, which is used to set the minimum signature level for any module which get loaded into the process. So you say, for instance, that if that value is equal to 8, then only DLL signed by Microsoft with Microsoft certificate can be loaded inside the protected process. And this control is enforced by ci.tdll, which check against the a field which is called announced key usage inside the certificate that has been used to actually sign the DLL to be loaded inside the process. As I was mentioning before, there are some protected processes that cannot be killed with administrator privileges, and these are the ones that are running with PS protected signer WinTCB, or as you can imagine, PS protected signer anti-malware, which is actually the level that most EDR or AV process are actually running at. And this is the level that allows is enabled by the blessing of the ELAM driver. Yeah, so these are all the data structure. You can we saw that inside the WinDebug, but you can do that programmatically by calling the ZW query information process and passing PS protection as an information class, and you will get the same information that we saw inside WinDebug. I was talking about also the signing level, and there is also defined here inside ntddk.h that, for instance, I was mentioning level Microsoft, which correspond to 8, and this is explained and clarified by those defines that are inside ntddk.h. But what we can see here, for instance, is also the protection level. So if we go back, we can do this for PPL, PPL, yes, and we can try to get also the signature level of the signer, which will be like this. So this means give me all PPL, and then like this. It will be like I equal to this, and then we want to go to the section signature level, which will be equal to p dot section signature level. Here then 0. going on here? Protection type. Yes, that's correct. Seems everything correct. Okay. Okay. Okay, we are back inside the previous view. Okay, we can do like this. I have some cheat sheet. We don't want to messing around with the X command. Okay, so essentially what I did here was getting all the processes with protection type equals to 1, which means PPL, and then I was getting the image name by casting to char* the Q kernel object image file name. I was getting the protection level here, and also the signer, which is the section signature level. So for instance, what we can see is that, I don't know, for services.exe, which is running as a PPL 61, so it corresponds to, should be WinTCB. The section signature level is 8, which means Microsoft signature. But for instance, if we see MSVM which is the main process of Windows Defender, we can see that it is running as PPL anti-malware 31. 1 means PPL, 3 means anti-malware, and that the signer is 7, which means actually, if we go back to the slide, that all the definition here, it's SE signing level anti-malware. So this is the correspondence between the two. And before loading a DLL inside, for instance, anti-malware, the ce.dll checks if the DLL being loaded has actually a valid signature level. So it should be anti-malware in the case of Microsoft Defender, at least. So we talk about PPL dump. So we know what is a PPL now, which are the requirements to have a PPL running. Now, just a couple of slides about the the vulnerability which is exploited, or the design flow, call it how you want it, that PPL dump is using. So the details of this are all inside the blog post of the author of the GitHub project. So you can find everything here. This is just a short recap, just to have background knowledge. So essentially, the exploit works by leveraging on the DLL search order. So there is this object directory, which is called known.dll, which stores preloaded images, preloaded of well-known DLL. So usually when you have, for instance, DLL inside System32, you don't want them to go through all the loading steps for each binary that is actually using that, because you will end up doing this kind of stuff for every binary which is being executed inside the machine. So what you can do to improve performance is just, place in memory a preloaded version and just let the process that is being loaded just get that DLL directly with all relocation stuff resolved, but also, and this is the important point, also the signature checks being done. So this is something different if you're running as PP, PPL, or unprotected process, because only in the case you are running as a PP, as you can see inside the picture on the right, top right, the file, the DLL, are actually being loaded from the file system. On all the other case, PPL included, this will be loaded from the known DLL if they are present there. So the idea is that if we are able to write an entry inside no DLLs, then we will be able to get loaded even our DLL, which is of course unsigned, even inside a PPL, because the PPL if the loader of the PPL find that that DLL is inside the no DLL path, then it will assume that the signature had been already be checked, so it didn't check. It will not check it again. The problem is that you need to be already a PPL, and in particular a PPL WinTCB process in order to be able to write inside that no DLL path. And anyway, in order to write inside the no DLL path, you need to use a specific function that will be mentioned in the next slide, but which is, I can spoil it, is the define DOS device. And this allows you inside to define a DOS device. This is something which is there just for backward compatibility, but we don't care much about it. What we care about is that depending on the user that you are running on, some symbolic link that you can define inside the Windows object directories will actually be resolved in different ways. So for instance, if you're running as a normal user, the slash question mark will be resolved in the path that you see in the slide, where all the X will be replaced by the logon authentication ID, a number that you can find inside the process related to the current user session. If you're running a system, that one will be resolved to slash global question mark, which has by chance a reference or a symbolic link also to the slash, so to the root WinObject folder. And this is an important point because this allows to exploit the vulnerability, because actually when you call the define DOS device, we are actually calling an RTC method which runs inside CRSS. And I don't know if you had were fast enough to see that, but CRSS runs as a PPL WinTCB. So actually the code is executing it by CRSS process when you call the define DOS device. And the point is that if you are able to force the implementation to follow the path that are marked in red inside the picture on the right, it will end up disabling impersonation, as you can see in the box on the right, which is called disable impersonation, surprisingly. And if you're able to reach that point, then no impersonation will be done. So the command will be executed as a system with the system privilege and by a PPL, which is running as WinTCB. And that PPL is actually allowed to write inside non-DLL path. And so what the implementation of PPL dump does, it just call the define DOS device, which is a protected process because they paid for the protection, and trick the CRSS process to write this event aggregation.dll inside the no-DLL path. And then the attacker can call create process with services.exe, which before the entry point will load some DLL, and among other, it will load the event aggregation.dll, but we will take from the /no-DLL path because we will find that, and it will not check the signature again because it assumed that the signature had already been checked by the initial loading process, and that will allow the event aggregation.dll process to dump even process that are running as PPL. The services after this, in the entry point, you just check if there is a global, let's say, mutex defined, because there can be only one single instance of services running in a machine. So it will exit, just terminate after that. So what we did actually by using our some tools and tweaks that we implement during our training, is actually avoid to be detected by the Windows Defender. We will see in a moment the effect of what we did on our binaries. Just the time to restore the detection snapshot. So okay. Oh, there is going to be bug. Okay. So we got an exclusion folder here. And here we have several instances of PPL. Each one has been recompiled with different flavors and different technique implemented. So the first one that you see here is actually the original one, the vanilla. Let's see. So if I try to move this, the root folder, you can see that Defender is going to complain about this in a few seconds. Here we go. Okay. So it says here that, yeah, this is the pdump/mtb signature which has been triggered. So we now know that the Windows Defender team has made a signature on this. Okay, that's enough. Fair enough. Okay, so it will be removed like shortly. There you go. Yes. Yes, you already told me. Okay, that's been removed. Work as intended. So this is a slightly modified version where we add just some dynamic loading of API. And again, I didn't finish to copy the DLL, and Windows Defender immediately stopped it from loading. But if I open this on IDA to see very broadly which are the differences, you can see that, for instance, we just focus on the import address table here and here, and you can see that here we are 115 entries, and here we are 92 entries. But if you look at the strings, for instance, you can find that they are all there. Actually, there are more strings than on the original sample, because there is also the string that will be used to load the dynamic loaded API, which you can find in the beginning of the string list that you can see here. But for instance, all the path, everything, all messages are here, and this probably the signature made by Defender points to that part. So we try to go a bit further with this, and we added some LLVM obfuscation without modifying actually the original code. So I will pop this inside the root. At least now I will be able to, I was able to run that. So I can move to C and try at least to execute the command. So I will pop. I should turn on my keyboard light, okay. -V. So, yeah. So now I was able to reach this point here. I'm dumping it with 768 because it is, if I'm not wrong, should be in this instance, of course, services.exe, maybe. Okay, let's do like this. Okay, we have here. Yeah, services.exe. No, this is we need it. 768 yes, that's it. I will try to dump it. Okay, I get it to dump. So no detection for the moment, but this is quite strange because there was supposed to be a detection here. So I'll try to do this again. There we go. Okay, we got a detection. But if we try to see how this was detected, we can see that this is a different signature. This is a behavioral signature. Indeed, our sample was detected at runtime. So something different happened, but it's not, of course, a clean way to go, but at least we got the dump here. So you also saw that the first execution was not actually detected at all. I mean, this was not the case for the second one. But just want to show you where we had the obfuscation, and just to link back to what Silvio was saying before. So if I just go to the main, so we added string obfuscation without touching the code. I repeat, just modifying the code through LLVM, and you can see here that there is this wonderful switch which has been modified by LLVM to contain, starting from the original code, of course, preserving the semantic of the code, of course. And this will, help to at least evade static signature, at least. And then also we left some strings here, but most of them you are not able to see that because they are simply encrypted. And this was enough to avoid the initial detection. But we got the behavioral detection. Let's come to the last part. Okay, so if I try to do this, dump again. Okay. So again, I was able to dump this, which is a dump of a PPL. I used PPL dump, vanilla, but we added some modification on it. And I got, with administrator privileges, I got a dump from a PPL. So you can imagine how this can be misused to do bad stuff. You can dump LSAS, you can inject a process which dump LSAS, you can just stay there and look for credential. I mean, you can do all the bad things that you can imagine you can do. So this is essentially a simplification of the tools, I mean, also conceptual tools that we provide through our training. I think this is the end of the story for today.
Basically, just let me add something. In the last sample that Antonio showed you, we applied the first 1.5 days of techniques that we showed to the class. It's we basically use the dynamic API resolution, removed encryption, LLVM, and a lot of some other small tricks that make evading the detection, as Antonio said. So, yeah, the approach that we use during the class, we also spend some time talking about and go deeper inside the security mechanism just to understand how they work in the way that it's not just blindly trying to evade, but just understanding what is going on from the other side.
Yeah, and also let me add that we have really a lot of labs. I mean, people that attended our training before is actually, feeling bad about how many labs that we give to them, but they are very happy because they can bring it home and keep studying and improving even after the training. And we think that this is a very good point to come to see what's inside the other part of the training that we didn't cover during this workshop. So because of course, because of time. So there were only 2 hours, which is a good amount of time to do a show, to give an idea, but then you have to, drill down and go in deep dive and have time to, elaborate things inside, concepts inside your minds.